I would like to start my talk drawing your attention to what we usually know as the climate emergency. This is not only the climate crisis, but also the climate emergency. And we know that we are witnessing frequent and intense extreme events such as droughts, heat waves, wildfires, heavy precipitation events. All these events together represent what we commonly know as climate extremes or weather extremes. But what the scientists are now realizing is that these events tend to occur jointly. So we can have a drought, and we can have, after a major drought, we can have heat waves, and droughts and heat waves combined can potentiate forest fires. And then after a long period of droughts and heat waves, we can have flash floods, for example, that will be much more likely, and the impacts of heavy precipitation. So the scientific community called these events as compound events and cascading risks. And this is really a problem, because one thing is a drought occurring isolated, and another thing is a drought occurring allied with a heat wave, heavy precipitation events, and so on. So just to give you some brief figures, losses in agriculture attributed to extreme events, because we are in a project related to agriculture, and according to the latest numbers or figures from the FAO, from the United Nations, we see that only due to droughts we have 37,000 million United States dollars of losses, which represent, in fact, 82% of the drought-related losses in all the socio-economic sectors worldwide. So this is a major impact. Droughts are really an important constraint for agriculture. Floods, 21,000 million United States dollars. Storms, 19. And wildfires, a much lower number, but here we should bear in mind that wildfires are prevalent in Mediterranean areas, in dry areas, and so the scale is much shorter. And still the problem of pests and diseases, that we cannot assess the problem of pests and diseases easily. So there are no reliable estimates of the impacts of pests and diseases. In terms of scientific evidence, I prepared this talk thinking that some people might not be completely aware of these basic climate change information, because we can have a very broad audience, but I think many of you already are already aware of these IPCC reports. The latest report was the synthesis report, already published this year. We have different reports for adaptation, for mitigation, and the latest report was a summary of these ideas. And I brought here just a very brief highlights from this latest report. It says that human activities, particularly through what we already know, the greenhouse gas emissions and the radiative forcing, have unequivocally, and this word is very important because it's very strong, caused global warming. So the scientific community has no doubts that greenhouse gases and human activities are leading to climate change, and global surface temperature reaching 1.1 degrees Celsius already above the pre-industrial levels in this period. So you see that we are very close to the 1.5 degrees of the Paris Agreement. Global greenhouse gas emissions in 2030 are related to the NDCs, and the scientific community is already realizing that the NDCs, and I've been working, for example, with Cape Verde, producing the NDCs, but for some countries in Africa, but the scientific community is realizing that the NDCs are not enough to limit the warming to the values defined in the Paris Agreement. So deep, rapid and sustained reductions in greenhouse gas emissions would lead to a discernible slowdown. This word is also very important. Slowdown in global warming within 2 decades. So this is not something that we have still some control in the process. Okay, so if we reduce greenhouse gases, we are still able to slow down the pace of this process. Compound and cascade events, already mentioned, are more complex and difficult to manage, and rapid and far-reaching transitions across all sectors, including viticulture and systems, are necessary. So we need a wide portfolio of mitigation and adaptation options. MONTEVITIS is precisely one project dealing with this part. Prioritizing equity, climate justice, social justice, inclusion, and just transition processes can enable adaptation and ambitious mitigation across actions and climate resilient development. So we have here also some important adjectives: equity, climate justice, social justice, inclusion, and just transition. So all these adjectives are very strong and very important to bear in mind. Finance, technology, and international cooperation are critical enablers for accelerated climate action. So this is a kind also of motivation for a project like MONTEVITIS, where we are acting towards these goals for a specific sector. In terms of the physical basis, this is not new. Svante Arrhenius, already in the beginning of the 20th century, said that a doubling in the carbon dioxide concentration will lead to a global warming of approximately 5 to 6 Celsius degrees. And this is really amazing, because we are talking about a scientist that lived a long time ago, without models, without computers, and in fact our projections today go very close to these values that Arrhenius already predicted. So we are just confirming the information that was already known for a long time ago. Guy Stewart Calendar said that climate is warming and carbon dioxide levels are rising a little bit later. And this is actually the paper he published. Look at the paper. April 1938 in the quarterly journal of the Royal Meteorological Society. The paper is available online. You can check the paper. So climate change is not a new science. There are papers from the beginning of the 20th century already reporting climate change and the problem of climate change. If we look at the carbon dioxide emissions, you see that in the Mauna Loa weather station or measurement station, we see a gradual and sustained increase, exponential increase from the 60s up to the present, and we are reaching year after year, day after day, record-breaking values of the carbon dioxide emissions and concentrations in the atmosphere. And we should also keep in mind that this station is in the middle of the Pacific Ocean, so very far away from China, India, Europe, and the United States, from the sources of pollution. I like very much this picture because it shows us the global carbon budget. We see that to the increase in the carbon dioxide, we have contributions from coal, oil, gas, and changes in land use. On the other side, we have the carbon sinks, and we see land and ocean being important, very important players that are preventing to have a stronger increase in the carbon dioxide concentrations in the atmosphere. So this is an imbalance, it's not a balance, because the sources are stronger than the sinks, but we have to work more on the sink side, but also on the sources side to try to equilibrate this scale. The greenhouse gas effect is also widely known from the past. Joseph Fourier and John Tyndall already reported the global warming system and also the greenhouse gas effect. So this is not new. And here, what we have, it's like a central, a thermoelectric central, where we have the burning of fuel. The burning of fuel is in the equator, and then we have the refrigerators at the poles. So what we are doing is capturing more and more radiation from the sun, which is our fuel, and we are putting more and more energy into the system, and the result is a shift of these circular trajectories, circular flows, Diavoli cells, Ferrel cells, and polar cells towards the poles. Just one remark. The current scientific consensus today is nearly 100%. So the idea that sometimes the newspapers say that the scientists are not agreeing among them regarding climate change, this is fake news again. Okay, so scientific community, I would say 100% of the scientific community agrees that the greenhouse gas effect is the driving force of climate change. Okay? For Southern Europe and Europe in general, we will have a decrease in the westerly winds, which correspond to the blue areas, and the red areas will have more westerly winds. Westerly winds are precisely the winds that come from the North Atlantic and bring moisture to Europe. So in the future, if we are having a reduction in these westerly winds, we will have less precipitation in Southern Europe. When we have an inversion of this dipolar structure, it's precisely what we are having now, and during the last 2 weeks, you have realized, if you look at the map in Europe, you will see that below the 45 degrees north parallel, from Portugal to Bulgaria, you have thunderstorms everywhere and showers everywhere. And in the north of Europe, you don't have precipitation, and you have a beginning of a drought in many countries in Central and Northern Europe. So it's the reverse of this pattern. Okay, so we have this shift from one to the other pattern. But in the future, unfortunately, this pattern we are now having will be less and less frequent. So Southern Europe will lose precipitation, while Northern and Central Europe will have an increase in precipitation. So, in terms of the historical trends, we have this well-known figure from Hawkins. It's a barcode, and we see that in the past we are experiencing a clear warming. Look at the latest years, the most recent years are record-breaking warm years with record-breaking temperatures, very warm years. At the time series of temperature, the same. This confirms the values, but when we look at the global mean temperature, we should not disregard that global mean temperature reflects also temperatures over the oceans. And the oceans are a significant part of our planet. So this global mean temperature time series it does not actually reflect what we are what we are experiencing over land. And look, for example, only for Europe, for European land masses, for the continent, we have a much sharper warming that already surpassed 2 Celsius degrees compared to the pre-industrial level. So we have already reached the maximum value of warming that was intended in the Paris Agreement, even though in that agreement it's foreseen to limit the increase in terms of global temperature. Trends are different depending on the area. We have the figure on the right is quite significant because you see that in Syria, for example, the warming is so strong, the recent past warming was so strong that, from my viewpoint, at least partially justifies the problems we are having in those countries because they don't have water, they don't have crops, everything was destroyed by the drought, and so people have to migrate, have to run away from that region because it's unbearable. It's so dry and warm that it's becoming unbearable for human livings. In terms of precipitation, we have a decrease, as we have already talked. On the left, we have annual changes in annual precipitation, and on the right, we have changes in summer precipitation. We see decreases everywhere in southern, but also in Central Europe. Central Europe will have a problem. Some countries, particularly Hungary, for example, or the Czechia now, will have problems with summer droughts. Even the last summer, I don't know if you recall, but there were major forest fires in Czechia and in Hungary as well, because they are having not only very warm summers, but also droughts. So they are starting to have the same problems as in Southern Europe. So this is one thing that should be also taken into account in the future. So the trends in the extremes are widespread in terms of hot extremes in the globe, more hot extremes, more heavy precipitation. Here, the Mediterranean area, there is no clear signal when we talk about heavy precipitation in the Mediterranean. So there is no clear evidence of an increase in precipitation extremes in the Mediterranean area in the last decades. Okay? But in Northern Europe, in Scandinavia, particularly in Norway, there is a clear trend for more precipitation extremes during the last decades. Agriculture and ecological drought. Again, the Mediterranean, a hot spot, but not only the Mediterranean. Last summer in Europe, record-breaking temperatures almost everywhere, but particularly in the southwestern Europe. Iberian Peninsula, France, Italy, the British Isles recorded the highest temperatures ever during the summer. Droughts in summer, extreme droughts almost everywhere. Rivers in Europe, many rivers were almost dried out, like rivers even in Germany, between Germany and Poland, in the border. or in northern Italy, the Po River and many other rivers in Europe were with very low flow rates everywhere in Europe, almost everywhere. So if we continue this pace, we will reach in March 2035 in terms of global temperature, the 1.5 degrees. And regarding climate projections, and Christoph will talk about this in greater detail, we have different scenarios, the SSPs nowadays, and different socioeconomic pathways that will represent different warming levels. I will not discuss everything here. I will leave the presentation. If you have these pictures available, also in the reports. For Europe, I've already talked about this, a decrease in precipitation in southern Europe, but not only in southern Europe. In some cases, in summer, the precipitation will significantly decrease. This is particularly the case of France. And heavy precipitation is also projected to increase almost everywhere, but in some areas of southern Europe, heavy precipitation in summer will not increase because we will not have precipitation at all. So if we don't have precipitation, we cannot have extreme precipitation events. So this is the case. So no, in some areas, no precipitation extremes in summer. Droughts everywhere, because even if we are having more precipitation in some countries, more in the north of Europe, we will have more evapotranspiration owing to higher temperatures, so the soils will have less moisture. And to end my talk, just briefly, because Elder Fraga will also present you more details regarding this issue. This is a study that we have recently done for Portugal, where we defined the denominations of origin of the different wine regions, and we assessed the changes, the climatic shifts in the conditions for the different regions. We can do a similar study for Montenegro, of course. And we see in different scenarios the different classes, the migration of the climate from one cool or subhumid class to a moderately dry or excessively dry, or from a warm temperature to a warm or very warm climate. So the trend is obviously from subhumid to dry, and from cool to warm or very warm. This is useful information for stakeholders, because vine growers can obviously learn the practices from different regions, see within the next decades which is the trend, and learn from the regions that are already having the same conditions they will have within 30 or 40 years. So this is important information. And finally, just to mention that before MONTEVITIS, we had the Clean for Vitis project with a white paper, and we have also a video. I think I don't have internet here. Maybe we can try.
Europe is the world leader in wine production, with a strong impact on its economy. The biggest challenge being faced is to reverse the negative effects that climate change and extreme weather events have on wine production. During the last decade, the increase in temperature has led to shifts in the grapevine's growing cycle, influencing berry ripening, wine composition, and typicity. This impact makes it necessary to develop very specific adaptation strategies, and thus reduce the impact of climate change in order to maintain the European wine sector competitive. In the short term, that is for 1 or 2 seasons, there are several strategies that help ensure a sustainable future. Appropriate canopy management helps delay the vine's development cycle and prevent the final stages of maturation from occurring during periods of high heat. To illustrate, a well-performed leaf removal can reduce water consumption and also postpone ripening until a cooler period. Applying sunscreen creates particulate films on the leaves, encouraging the plant's metabolic growth and reducing sunburn during periods of high heat and water stress. The use of protective nets also reduces sun exposure. Supplemental irrigation. Given the growing scarcity of water resources, irrigation must be implemented with water savings in mind, while still complying with the production rules of wine regions in order to maximize its benefits. Drip systems optimize the amount of water allocated to each vine, while plant water status indicators can be used to optimize irrigation scheduling. Soil management. The use of specific plant species used as cover crops in vineyard interrow spaces contributes positively to soil fertility, depending on whether we are in a dry or wet season. Some plants compete very little for water and promote soil fertility and health. This all helps maintain the vine's vigor and prevent soil erosion. Pest and disease control. The control of pests and diseases should be constant, since climate change may exacerbate them. Long-term adaptation strategies comprise of all the measures that require structural changes of vineyard system. Training systems. Long-term strategies start with changes in training systems that should encourage heat and drought tolerance, reducing the accumulation of sugar content in grapes, and lessen the impact of temperature and radiation in the cluster zone. Scion rootstock combinations. Another important measure to adapt to climate change is the selection of suitable scion rootstock clone combinations to preserve wine's typicity while delaying grape ripening to better deal with the increase in summer temperatures and dryness. Although challenging, the goal is to find new varieties and clones that are more resistant to dry and very warm climates. Vineyard relocation. In more extreme cases, the relocation of vines to higher elevations, coastal zones, or areas with low sun exposure may be required in order to take advantage of more favorable climate conditions. Climate change is here, and educating the consumer to gradually adapt to different styles of wine resulting from modified terroirs is also very important.
So I think the message is clear that climate change is not a fatality. So we can act in terms of mitigation of greenhouse gas emissions, of course, but we can also do some adaptation, climate change adaptation, which is very important, but should be developed for each sector separately. And in viticulture, as you saw in this movie we prepared in MONTEVITIS, and I hope we can do something else in the same way in MONTEVITIS. We have many tools, many options in the vineyards to adapt to climate change. Okay, so we can act in both directions. Thank you very much for your time. And as I said, I will be here throughout the day, so for any question, any issue, we can talk later. Okay? Thank you.
Great. Okay, thanks. So after this nice introduction of climate change and the climate change impacts for Europe, I would like to go one step backwards and introducing you into the tools that are used to get this information about the future climate change, and these are climate models, global and regional climate models. And the idea here to have this presentation a more lecture-like character. The idea is here to introduce you to these models, how they function, and also present you with information how to acquire the data from these climate model projections, and also introduce you to some tools that can be used to pre-process and analyze these data. So first I would like to start with a little tour in history. So the equations, the basic equations that basically drive the atmospheric systems and are solved by the climate models are the so-called primitive equations of atmospheric flows. This is a system of differential equations, and they are quite complex. However, you can at least conceptualize them or in a broader way understand them as conservation laws. So we have 3 different conservation laws in physics. One is the conservation of mass, or in physics we call this the continuity equation. Then we have the conservation of momentum, also called the Navier-Stokes equation, named after Claude Navier and George Stokes, who are basically just 2 people that developed these equations. There were actually many more, like for example Poisson, that also developed this equation, but I mean that's history. For some reason things get named after the famous scientists of their era. Then we have the conservation of energy, here in terms of the temporal evolution of temperature. And as a 4th equation, or a 6th equation better, we have the ideal gas law that translates between pressure, density and temperature. Okay, this whole system of equations, in total we have 6 equations here, were first formulated by Willem Bjerknes. And what we have here is a system of differential equations for 6 prognostic variables. So we have air density, we have 3 velocity components, we have air temperature, and we have air pressure. So we have in total 6 variables and 6 equations. So just remember that the conservation of momentum, the Navier-Stokes equation, is actually a vector differential equation, so it represents 3 different equations. So we have 6 prognostic variables, and we have some external and internal drivers of the climate system. This is the drag force, the drag force, then the latent heat, so the heat that is captured in the phase transformation of water. Then we have the radiation here. We have the angular momentum and the gravity of the Earth. So this system of equation were first formulated around the year 1900, but it takes another 20 years until the first time when it was solved. And one thing I would like to mention, this system of equation is really powerful. So it can solve, for example, the whole atmospheric flow of the Earth atmosphere, but it's also able to simulate or solve the flow on a much smaller scale, like here, for example, for a cyclone, or even for the circulation, the atmospheric circulation around a building, or the climate inside of a room. So everything could be solved by this system of equation. So as I said, it took more than 20 years until this equation actually gets solved. And already Bjerknes said that the weather prediction should be based on these physical equations. So it should be based on numerical weather prediction. However, in the 20th century, the weather prediction was more or less based on experienced meteorologists who basically look at the weather patterns and then by experience could decide, yeah, in this region we will have like 20 degrees under this weather patterns, and in this region it will be colder. So it was just by experience and not by any kind of physical reasoning or modeling. And the first guy, yes, the problem why it was not numerically solved until the year 1920 was because our external and internal drivers are quite complex, so we need to find a way to represent them in the equations. And also, we are dealing with partial differential equations, and we need to approximate them with some numerical scheme. So these two problems needed 20 years to get solved, and the first person who solved this equation was Louis Fry Richardson in his book from 1922, Weather Prediction by Numerical Processes. And here you can see basically the European continent, and each box is the grid box that he solved this system of equation on. And what he actually did is he not solved for the equation for the whole European continent, but just as an example for two grid points. And he also performed this calculation just over a period of 6 hours. He started to write the book in 1915, actually, so 7 years before it gets published. So it took him quite some time to formulate the equation and solve it for two grid points over 6 hours. Actually, he solved this equation or calculated everything in the year 1916 when he was serving in the military during the First World War. And he was an ambulance driver, having quite some time to do the calculations. And it is said that for this 6 hours of calculations, so he calculated just 6 hours, it took him 6 weeks to perform the calculation. Because, there were no computers, so you have to do all these calculations just by heart. But he was able to extrapolate, and his extrapolation was that if it would be able to have 64,000 computers, and by computers he means human computers, so humans that perform calculations, it would be able to perform a weather prediction for the whole globe in a reasonable time. And I quite like this picture here that shows how this would look like. So we have here the globe with every little grid cell, and then on each grid cell we have a room full of human computers that just calculate the weather of this single grid cell. So this would be then a meteorological service based on 64,000 people. So it was just impractical. One reason was because, it took 20 more years before the actual computer was invented. And then it took even 20 more years until the first real climate simulation was conducted by Ryukuro Manabe, who actually got in 2021 the Nobel Prize in Physics for this accomplishment. And in the year 1965, he created the first global climate model simulation on the world's fastest computer of this time, situated in Princeton in the Geophysical Fluid Dynamics Laboratory. And so this is a picture of the computer, and these days it was the fastest computer at the time. However, if you compare to nowadays computational resources, your smartphone is around 1,000 times faster than this. However, the climate model simulations still needed high performance computational resources, and I will show you later why this is the case. So the model of Manabe was just an atmospheric simulation model, so it simulates the atmospheric flow. However, they pretty fast realized that the climate system is based on more than just the atmospheric flow, but you also have to consider other compartments of the Earth system. And this is, for example, the ocean. So in 1969, Manabe, together with Kirk Bryan, developed the first so-called atmospheric ocean general circulation model. So a model where the atmospheric processes and the ocean processes are coupled together. And I mean, we don't have much computational resources at the time, and this was basically here what the Earth looks like in a very broad way in the model. So we have a huge part of the globe is land, and then we have a rectangular sea on Earth. And the model performed the atmospheric circulation calculations to solve the primitive equations. And despite the fact that it is not a very accurate representation of the Earth, the results were quite convincing that we're on the right path. So what I show you here are on the left-hand side the computed results, and on the right-hand side the observed results. And on the x-axis is what we call a zonal mean. So for each latitude on Earth, from the equator to the poles, just the average over all longitudes. On the top, it's always the atmosphere, and on the bottom, it is the ocean. And what this model was already able to capture are the basic features of the atmospheric system. So this shows you temperature, and we have, if you go from the equator to the poles, we have a reduction in temperature, so it gets colder and colder, like it is in the observation. We also have decreasing temperature if we go higher and higher, until we get to the tropopause in the stratosphere, where we have a temperature inversion, and this temperature inversion is also captured by the model. And if you go to the ocean, we also have this temperature gradient from the equator to the poles, and also a reduction in temperature if you go down into the ocean. So the basic features were already captured by this model from Manabe and Bryan. Now I would like to show you the simulation of one state-of-the-art global climate model. So we make basically a big jump until to the last years. And what you can see here is a simulation of one model. Actually what you see, the grid boxes here, are really the grid boxes of the model. So this is the resolution of a state-of-the-art global climate model simulation that also entered the IPCC reports. And what the model does is it basically creates a transient evolution of the atmospheric system. So it really simulates day by day by day. And what is shown here is the monthly average values. So these are the monthly average values. So basically you see the seasonal cycle of temperature, where you have a northward progression until the middle of the year with higher temperatures, and then again a southward retreat of the high temperatures. Okay, so this is just to show you how the climate model results at the end look like. So to give you a little overview how the state-of-the-art climate models function, we have, as I said, the world is divided into grid cells, three-dimensional grid cells, And on each of these grid cells, we solve our primitive equations and get results for our prognostic variables. So temperature, air pressure, air density, and air velocity. However, we have to solve also, or calculate also, for each grid cell, our internal and external drivers. So radiation transport, for example, has to be solved for each grid cell separately. And we also have an additional problem that I showed you, that the primitive equation can basically solve the atmospheric flow over a large scale. So it can also solve turbulence. However, if we have a grid cell like this, some effects like turbulence, or for example also the formation of clouds and precipitation, cannot be solved on the grids, on this whole grid. However, it needs to be solved with a so-called parameterization. So basically the internal and external forces, and also the subgrid scale processes needs to be solved additionally on every little grid cell. So at the end, the global circulation models can simulate the climate system and considers all physical and biogeochemical processes. So these are the state-of-the-art models do this. The typical resolution of these models is around 100 to 200 kilometers, and the temporal resolution is somewhere in the neighborhood of minutes to half an hour. And it is actually coupled to the spatial resolution. So as I said, we still need supercomputers, high-performance computing, to perform simulation with such kind of models, due to the fact that we have to solve the partial differential equations on the whole globe, and then we have additional calculations on each grid cell. So the climate models get, the reason why we still need high performance computing is because the climate models get more and more complex. So here we are in the year 1969, where we have our Manabe and Brine model, and which has atmosphere, land and ocean. And then in time, more and more processes and more components of the Earth system gets added to the climate models, so they get more and more complex. So in the 1980s, we added ice. In the 1990s, we did a major step from having a swamp ocean, so an ocean without any current, to an ocean which actually has a dynamic, so has ocean currents. We also added lakes and rivers that discharge into the ocean. Vegetation were somewhere added in the 1990s to 2000s. Then also the atmospheric components were more and more complex. So aerosols were added. In the 2000s, we added also carbon aerosols, which are more complicated to simulate because carbon interacts with the humidity in the air. So in time, the carbon aerosols can change and also change their optical properties. We also add smaller components like dust or sea spray that also interacts in the atmosphere. And in the years 2010 to 2020, we also added marine life forms, so a very complex ocean. And this is necessary because these models then at the end want to solve the whole carbon cycle. So how carbon is transformed in the atmosphere and taken up by the ocean, for example, or extracted from the ocean. One word of caution, maybe you see here that clouds and precipitation is here in the 2010s. Clouds and precipitation were not just present after the year 2010, so already the earlier models also have cloud and precipitation. However, the horizontal resolution of the models gets high enough that you can solve clouds and precipitation now on the grid cell and don't need to fully parameterize cloud and precipitation formation. Now, this whole development continues in the future, and just to give you a short overview of the changes that are anticipated or scientists currently working on, these developments are basically under the umbrella of trying to increase the efficiency of the models. As I said, they are really high complex, they need high performance computing, and now people look for a way to make them more efficient, so that we can increase, for example, the resolution. So here the major streams of development are basically on the software side machine learning emulators, so trying to exchange one of the more complex physical parameterizations, like for example radiation, against a machine learning model, so for example a deep neural network. Then there's also the idea of, or the development of using so-called physics-informed neural networks, so trying to solve the partial differential equations, not with some numerical scheme, but with a neural network. Then on the hardware side, there are basically two developments. One is trying to use GPUs, so graphical processing units, to solve the equations. And the other is to use quantum computer, either to simulate the partial differential equations themselves, but also to use quantum machine learning to perform some of these machine learning emulated tasks. So this development is driven by major model intercomparison studies, and these model intercomparison studies in global climate modeling are called climate model intercomparison projects, and there are the most important here are the last three: CMIP3, CMIP5, and CMIP6. The simulations that were conducted under these intercomparison studies also enter the IPCC reports that João just mentioned. One major part of the climate model I just skipped so far, and this part are the so-called the socio-economic scenarios. So to project the climate of the future, we need to know how will the socio-economic system evolve in the future, how much greenhouse gases will we emit, and this is basically what we get from these scenarios. And from CMIP3 to CMIP6, these scenarios changes in time because we learn more and more about the socioeconomic system, of course, and also learn more about the greenhouse gases, about the different greenhouse gases. So we have to constantly update these scenarios. The latest IPCC report uses the so-called shared socioeconomic pathways, or SSPs, which are basically storylines for the future development. And they are important because they represent the major uncertainty of the global climate projections. So there are 5 different SSP scenarios developed for the IPCC report. One is the SSP1, which is a sustainability scenario, taking the green road. Then we have a middle of the road scenario, a scenario that is characterized by regional rivalry, one that is characterized by inequality between countries and within the social system. And we also have the worst possible scenario, I would say, the fossil fuel development, where our development still is based on fossil fuel consumption. So how does these scenarios enter the climate models? So this is shown by by this plot. And we have here our SSP scenarios, so SSP1, 2, 3, and 5. The other numbers are not interesting here. And what is done is we use socio-economic models to drive with these scenarios, and these socio-economic scenarios give us then emissions. Emissions of CO2, of methane, of nitrous oxide, and of sulfate, and any other greenhouse gas. And the climate models does not care about the emissions. What is interesting for the climate system are the concentrations. So how much greenhouse gas is accumulated in the atmosphere at a given time. So we first calculate the concentrations, and these concentrations can be then translated into a radiative forcing. And this radiative forcing is what enters our climate model. So we calculate the radiative forcing, and then our climate model can be driven with this radiative forcing and give us a global warming system. Now the more modern global climate model also have a dynamical carbon cycle inside, so they can calculate how much carbon can be taken up by the ocean, for example. And if you have a warmer ocean, you will have more emission of carbon from the ocean into the atmosphere. So we have an additional dynamic component for CO2 emissions. So we have basically a feedback that in the model that acts again on the concentration. So the state-of-the-art models basically also simulate this feedback here. And then we have at the end a global warming signal, which is translated by the model into regional climate change, as João showed you. Okay, so that looks quite good so far. However, if we want to perform regional climate change impact analysis, we have one major problem, and this major problem is shown here. So this is again a state-of-the-art global circulation model, and this is orography that is shown here. And you can see that the orographic features of the European continent are not very well captured by this model. So Italy is hardly present, the Alps are vague, and if you go and simulate with this model for example, precipitation, like it is done here on the right-hand side, you can see that it's basically some strange patterns. If you're interested, for example, in extreme precipitation for a specific region, this resolution is just too coarse. You cannot, at a reasonable detail, tell anything about precipitation on a specific location with this model. So what we need is higher resolution, of course, and the solution to this are so-called regional climate models. And the idea of regional climate models, and you see again here one simulation, is that instead of simulating the whole globe, we just simulate a specific single limited domain. And in this case, it is Europe. And like our global climate models, these models simulate exactly the same. So still they solve the primitive equations, and they give us a transient time series. Here again, temperature, monthly average temperature. So again, we see the northward progression and the southward retreat of temperature. However, it simulates it on a much, much higher resolution. So you can see the orographic features also of the Alps. So they are much better. So at least for regional climate impact analysis. The idea behind regional climate models is to simulate just a limited region. And since the climate system is a global system, we need at least the information from the global climate system at the boundaries. Okay, so we usually have the conception that we have a global climate model that simulates the evolution of the global climate, and then we have a regional climate model that is nested inside of this global climate model to simulate the regional climate at a much higher resolution. So these climate models are called regional climate models, or short RCMs. They are in conception basically the same as global climate models. They use the same equations. They even use the same methods or modules from global climate models. However, they only solve it on a limited domain. So we have a trade-off, having a higher resolution, but therefore we simulate on a limited domain. The typical spatial resolution of these models is 1 to 50 kilometers. There are also simulations around 100 meter available, or done at least. The temporal resolution is in the lower minute scale. And as I said, to drive these models, we need global climate models. So everything looks quite good. However, these models have some problems that needs to be taken into account. One thing is the regional climate is driven by the global climate model. So we have an energy and mass input from the global climate model into the regional climate model. So the climate change signal that the regional climate model simulates is more or less driven by the global climate model, because it gives the energy and mass into the system. And also we have one problem that needs to be taken into account, and these are boundary effects. So we simulate a limited domain and drive it by a global climate model, and this will cause boundary effects. And here you can see one boundary effect. For example, this is precipitation bias. So the difference between the simulated precipitation and the observed precipitation for this domain. And you can see at the boundary of the domain, we have artificially higher precipitation bias. And this is really the boundary effect. So if you analyze, for example, regional climate model simulations, you have to take into account that your analysis should be not too close to the boundaries, because you might have these effects there. Okay, but the simulations look much, much better. So here we have the orography of the GCM, and the orographic features of the RCM of the regional model are much, much closer to reality now. Okay, and also if you look at the precipitation formation, it has a much, much better representation of regional precipitation, and you even see sometimes here cyclones that move over the region. So if you want to perform regional climate change impact analysis, you should use regional climate models. Now, two more things I would like to mention here. First, if you like to work with the climate model data, then the question is, where do you get these data? And there is one problem, and this problem is the volume of the data. So we are talking about huge volume of data. So CMIP3, which was published in the year 2007, or around the year 2007, has a volume of 35 terabytes. So this is handleable by modern computers. But if you go for CMIP5, CMIP6, or the regional climate models, here Cortex, you talk about the petabyte scale of data volume. So it's much data. And there exist several data stores to gather these data. There's, for example, from the European Union, there's the Copernicus Climate Data Store. There is from the British Atmosphere Data Center, there's a platform available. Then from the German Climate Computing Center, there's a database, the World Data Center for Climate, and also the colleagues in the USA have a data archive at NCAR in Boulder. And And the problem is that depending on the country where you are situated, these data centers might be far away and the connection will be very, very slow. And therefore, during CMIP 5 generation, the scientific community established something that they called the Earth System Grid Federation. And this is basically a system of, or a community of different data nodes where they store CMIP data and also regional climate model data, basically. And the idea is to have several different nodes over the globe in different regions where you can download the data from your current location, and between the node there's a data exchange. So the idea is that each of these nodes here, and there are like I think 10 to 20 nodes available globally, and the idea is that each node will have the same data. So even though when one of the nodes has a maintenance issue or is dead, you can go to another node and download the same data from another node. So these are the basic sources. So what are the tools for climate data? There is one issue, but there's one major issue here. So you need a computer, of course, and you most likely also need programming experience to analyze and pre-process the data. And because most of the tools are developed for the high performance computing environment, you also need experience with Linux usually. However, there exist various tools to analyze, visualize and pre-process climate model data. And one advantage that we had in the climate model community is that we use a common data format. And this is the network common data format, NetCDF. So basically every modern climate model data, either from global or regional climate models, will be in the NetCDF format. And all the tools are basically able to handle these formats. So we have, for example, for the pre-processing and analysis, we have the climate data operators or the NetCDF operators. We have GDAO functions. And for visualizing, there are also some tools available like Panoply, GRATS, NCL, NCView. So there's quite a lot of software available to access and pre-process NetCDF data. And there's a web page from the UCAR, from the University Corporation for Atmospheric Research, that lists like 50 or so tools you can use for access and visualize the data. And there are also libraries available for all the famous computing languages or programming languages like Fortran, for example, that is still present in the scientific community. C, Java, also for the script languages like Python and R, there are packages available that can read NetCDF files. And if you work with geoinformation system, these nowadays also implement libraries to access NetCDF files. However, if you don't want to do this, then there are some platforms that can be used online just to visualize modern climate model data. And there's, for example, the interactive atlas from the IPCC, which covers all the pictures of the last IPCC report, of the sixth assessment report of the IPCC. There's also a portal from the World Bank that also gives you climate change impact results on countryside level. The Potsdam Institute for Climate Impact Research has also a platform that visualized all the data we had in several projects over the world. So for separate countries like India, Germany, Peru. where we have stored climate change impacts in terms of agriculture, water cycle, tourism, so quite a long list. And there's also the Climate Explorer from the Dutch colleagues. And this platform, besides giving you visualization of climate model data, you can also use to download several observation and also global and regional climate model projection data. Okay, and as last word, if you're interested in learning more about regional and global climate modeling and how to use the data, I would recommend the Climate Data Guide from the University Corporation for Atmospheric Research, which is a corporation of 122 universities and institutes in the US, and one of the institutes is also the Arizona State University, and they collected here a guide that gives you information about climate data, about the climate system, and you can search for tools, and they also provide you with trainings, for example, on regional and global climate modeling and climate impacts. Okay, and with this I would like to end and hope for some questions.